Is it visible now?
Yes.
Okay. Okay. So first of all, thanks to the organizers. And today I will be talking about modified celestial amplitude in Einstein gravity. This talk is based on the work done in collaboration with Shamik Banerjee, Sudeep Ghosh, and Arnab Saha. So the outline of the talk is as follows. First, I will briefly talk about what are the conventions which we will follow. Basically, we will see what will be the variables used to parameterize the null four momentum and the three-dimensional asymptotic space-time. And then we will see how these variables transform under the Poincare group. And then I will mention what are the Mellin amplitude and how we define the modified Mellin amplitude. So these are basically the change of basis for the scattering amplitude, and I will also mention what are the motivation for doing this change of basis. Uh, Now then I will mention about the conformal factorization. So this is the analog of the soft factorization of scattering amplitude in the case of the Mellin and basically the celestial amplitudes. And finally, I will sum up with a specific example of four graviton scattering amplitude, how all these things come together. So let's begin. So in the for the Lorentz group, the SO3, 1, this is isomorphic to SL2C. So now using the polymatrices, we can go from the vector representation P mu to the SL2C representation P. Now this will be this capital P is the representation of four momenta in SL2C representation, and this is how we define the norm. Now under Lorentz transformation, it transforms in the following way, and we see that determinant that is the norm is conserved. So now the null momenta can be parameterized in the following way with the help of these three parameters: omega, which is the energy scale, and the z and z bars. So the z and z bars, these they parameterize the 2D space of null momenta direction, which is the same as the celestial space, which we will see in the next slide. So so we have parameterized the null momenta, and these parameters under the SL2C, they will transform in the following way: omega goes to this factor and z goes to this. So this z we see is this transformation is the same as the global conformal transformation of zz bar. That is just to say that Lorentz group acts as the global conformal group of the celestial space, which is z and z bar. So now we have we till now we saw how we parameterize the null momenta, and now let's see how we will parameterize the three-dimensional asymptotic space-time, the null infinity. So null infinity is labeled using the Bondi coordinates u, z, and z bar. Here z and z bar are the coordinates of the celestial sphere, and u equal to t minus r is labels the retarded time. So again, as I said, that space of null directions and the celestial sphere are the same thing. And under Lorentz transformation, these Bondi coordinates transform in the following: the u goes to and z goes to this. And under space-time translation, z maps to z and z bar go to the same thing, and u goes to this function, which can be written so this factor has is without z and z bar and z bar. So we saw that the Lorentz group acts as the conformal group on 2D celestial sphere. So we want to express the scattering amplitude in a basis where it admits some interpretation as a 2D conformal correlator. So we write the S matrix usually in the momentum space and in the plane wave basis. Now, since we want it to be represented as a 2D conformal correlator, We choose a conformal primary basis instead of the plane wave basis. Now this change of basis from the plane wave to conformal primary wave is implemented by this Mellin transformation. So we integrate with respect to the energy scale of the null momenta, and this S is the usual scattering amplitude of mass zero massless particles, and where the momenta is parameterized with the omega z and z bars, and this is the helicity. And we integrate, so we are integrating over all the energy scale. Now, so it's by the way we wanted, so that the how we define it. So this transforms indeed like a correlator of conformal primaries under the Lorentz transformation. Here the lambda which we have introduced here, so they relate to the scaling dimension in the following way. The scaling dimension delta is 1 plus I lambda, and the conformal dimensions are given by delta minus sigma, and delta h bar is given by delta plus sigma by 2. So yeah. Now why we want to go from the Mellin basis to the modified Mellin basis. So the motivation for that can be like with this example. So take a case of massless scalars, and the Mellin amplitude requires the conformal primary basis. So the solution for the Klein-Gordon equation will look something like this. And we see that the particle will be localized at q dot x equal to 0. And all the particles, when we write the Mellin amplitude, they are localized at on the same null hyperplane, which is q dot x equal to 0. And here qzz bar is the unit null momenta. So for the modified Mellin amplitude, we will consider a basis in which solutions can be localized on different null hyperplane. So here we add a factor of u in the denominator in the conformal primary wave, and now the particles can be localized on different null hyperplane, because this u will be different for different particles. Now how this transformation, this change of basis actually looks like. So up to this factor, it was the same for the this S here is the scattering amplitude. And we have for the modified, we have added this exponential term extra to now this exponential factor also helps with the regularization, and with this shift we can keep the integrand with respect to omega well behaved for a large value of omega. So this is the regularization term e to the power minus delta s. As we said that the Mellin amplitude, we thought it to be defined on the two-dimensional celestial sphere zz bar. We can think of the modified Mellin amplitude as defined on the null infinity uzz bar, and this is manifest from its transformation property under the full Poincare group, which is given by this. So under the Lorentz transformation, the modified Mellin amplitude transforms in the following way. And under the global space-time translation, it transforms in the following way. So we saw that the Bondi coordinates transformed. So this is the same way they transformed. And under the global space-time translation, we saw that the u went to is something like some factor of z, z bar, z bar, and some constant, and z, z bar map to themselves.
A quick question.
Yeah.
Under the BMS transformations, how do they transform?
So I will under the so these are defined on the SEA, but in yeah, the transformation operators. So they will be defined in with some as some function for, like, for example, the super translation. They will be like some function of some factor of z, z bar, and del by del u kind of thing. So that will be the what operator will look like.
That's
so
correct,
for super translation, this f will be like it will be a generic function, f z, z bar.
I mean, has it been worked out?
So I have not worked that out, but I think the general operators have been worked out.
Okay, maybe we can discuss in the discussion session.
Okay. So now coming to the conformal soft theorem. So the energetic soft theorem can be given like this: omega going to zero, the energy scale, and the n particle scattering amplitude goes to some factor, and the n-1 particle amplitude. The analog for the soft theorem for the celestial amplitudes is the conformal soft factorization, where we take the limit with respect to this the lambda factor we introduced to be 0. So these are just the leading energetic and conformal soft factorizations. Now, so in the conformal soft limit, the modified Mellin amplitude is related to the energetic soft limit, where we use this relation to get a delta omega. So when we put this conformal soft limit, so inside this integral we get a delta omega. So, and this Sn is the scattering amplitude. So this is related to the energetic soft limit, and this is the conformal soft limit. Now to use this relation to get a delta omega, we require that the integrand should be well behaved for large omega. So in the case of the Mellin amplitude, the requirement is that the momentum space amplitude should be falling at least as fast as omega to the power minus b, for b some positive number. But for the modified Mellin case, we have the exponential regularization term. So the UV behavior of momentum space amplitude is not so restricted. So coming to the example, so this is the scattering amplitude for the MHV amplitude in Einstein gravity. The main thing to notice here is that here this condition that omega to the power minus b, the scattering amplitude should fall as like that. So that is not met because omega are more in the numerator. So the Mellin transform of this amplitude from momentum basis to conformal basis is divergent. But that is not the case for the modified Mellin case, where we can define the conformal soft limit because we had the regularization term. So the integrand remains well behaved. So the integrand remained well behaved because of this regularization term, and we get the following conformal soft limit. And So here we see that under translation, this is the u is z mapped to themselves, and this is the only u factor we have, and this remains invariant under translation because this whole factor, so the change in it is proportional to z minus z bar, and there is a delta z minus z bar constant. So now the conformal soft factorization. So we get, as I said, that we will get a factor like this, del by del u kind of term, acting on the n minus 1. So we had the soft limit taken on the first particle, on the n minus 1 particle amplitude. And this is because we took, so this was the leading limit, and leading soft graviton is the word is the word entity for super translation. So appearance of del by del u is just an indication for that. So finally, conclusion that the similar calculation can be done for gluon amplitudes as well, and and we saw that the modified amplitude behaves like a correlation function of operators inserted at different points of null infinity, like so the three-dimensional space u z z bar. And in the modified representation, so the time evolution is more explicit compared to the representation in Mellin basis. I think it was also discussed on day 2 in the discussion session that the time evolution in the Mellin amplitudes, the celestial amplitudes, is encoded in delta I, the scaling dimensions. But here in the modified representation, this time evolution is more explicit with you. So with this, I would end the talk. Thanks for the attention.
Thanks, Pranjal, for finishing before time. Question, Som.
So is there any way you can relate these amplitudes to the Park-Taylor amplitudes for the MHV amplitudes concerning gluons, for instance?
So this similar calculation can be done for gluons, but how to relate to so for the MHV gluon amplitudes, and yeah.
So I mean they should be related, right, in some way, because for the MHV amplitudes we know that the Park-Taylor result is the actual result.
Okay, so I don't know what to say. So I have not like worked out that relation. So yeah.
Okay.
Are there any other questions? If not, let's thank Pranjal again. Gourav, are you there?
Yes, sir. Yes, sir. Thank you. Hello. Hello. Hello.
Yes, I can hear
Okay.
you.
Okay.
Yes.
Thank you, sir. Thank you for the organizer for providing this opportunity. And first, let me
You can share your screen.
Yes, sir. Screen share. Okay. Now to my